master degree from NIT Rourkela, and then he worked as an engineer at INRIA, France, and he has also worked as positions like project fellow at NIT Jaipur, research fellow at INRIA Sophie Antipolis, France, Sophia Antipolis, sorry. And his research interest is in computer vision, video computing, anomaly detection, medical imaging, and image processing. He has published several articles in top-tier conferences like CVPR, WACB, AVSS, ICONIC, and so many. He is currently serving as a reviewer in such top conferences like CVPR, WACB, ECCB, AVSS, and FG, which is really a big thing for a young researcher, right? To dream open and publish a paper in CVPR, and he has recently published, and one of his paper basically accepted in the world's best conference CVPR, and his paper has also earned highlight paper distinction, which is really a great contribution. So we are pleased to have you today, and I request you to share your experience or insights on foundation models which can be used for medical image segmentation. Over to you.
Thank you so much, sir, and giving this kind of introduction. Okay, I'm really happy to be part of this program. Okay, I'm gonna share my screen, and precisely I have 1 hour, I guess.
Yeah, 1 hour.
Right now. Okay, all right. Okay. So I share my screen.
Yeah,
Okay.
it's visible. You can just make it full screen. Yeah.
Okay. So
Yeah, it's visible. You can start the session.
okay. So hello everyone again, and good evening to the people in India right now. So the today's talk is mostly about foundation model and for medical image segmentation. So foundation models recently they are everywhere. I mean, they are in the all across the computer vision, NLP problems. Many of us, we heard about these GPTs, llamas. These are all nothing but foundation models. They are doing great in NLP task. So there are also similar things in the computer vision. And how do we use this kind of things in the medical image segmentation? So that is the main objective of this talk today. So yeah, okay. Why is it not changing? Okay. So medical image segmentation. So I'll just try to be briefly define this part. Okay, what is this segmentation problem? If we have an image, let's say we have a brain MRI image or brain CT image. If we want to partition the image into some distinctive subsets, maybe the subsets could be overlapping or disjoint. So basically, if we want to partition the image into different regions, we call it as the segmentation, right? And a typical deep learning framework that can do this kind of task is that follows an encoder decoder structure. The encoder, let's say, it takes a source MRI image, encode it to some latent vectors, and from the latent vectors, the decoder decode the image into some prediction mask. And these encoder decoders during the training process, they are guided by the ground truth segmentation mask, and the objective is to minimize the error between the prediction mask of the decoder and the ground truth segmentation mask that you might obtain from a clinician, right? So if we have to zoom in into this particular framework, the key lies here is the encoder and the decoder. Okay, maybe there could be several approaches for fully supervised segmentation, weakly supervised, semi-supervised, this and that. But let's focus on the encoder decoder part. What is their responsibilities? So the encoder, it takes the input image. The input image could be RGB, MRI, CT scan, HRCT images, this and that. So the encoder, the responsibility of the encoder is to capture the fine-grained low-level cues of the input image and project them into some latent vectors. So the latent vector has the highest information preservation from the input image, and this is used for the decoder that stage by stage it decodes into some segmentation mask of the ROI and the region of interest, right? So, but the thing is, why do we need this medical image segmentation task? So maybe the segmentation task could be the first step of several other downstream tasks. For example, if we want to recognize or detect a particular kind of disease, for example, the lungs infection, maybe caused by COVID-19, this and that. So if you have a image of the lungs, the entire region, the first step is to segment the lungs area. So a typical network could be a unit, which is widely used. And after the segmentation task, only the region pertaining to this lungs area are used for a classifier network to say that whether it is COVID-19 or not. So by having a segmentation task, it kind of increase the efficacy of the model to a pretty high level. So having a good segmentation model is helpful for many other tasks. Okay. So what are the common methods? As I have already taken this name UNet. So UNet is mostly, or maybe it is the foundation block of this segmentation task. So it also has it also follows a encoder decoder structure. So on the left, if you see, it takes an image that encodes into some latent vectors here, let's say 1024. And from the 1024, it tries to decode by upsampling, deconvolution to generate this kind of segmentation mask. But the key thing between a autoencoder and a UNet lies here is the skip connection. The skip connection between the each level of the encoder to the each level of the decoder. So this allows the information pass. So as I say, the encoders are pretty good in capturing the low-level fine-grained information. For example, the boundary of the regions, the texture of the regions. So how to propagate or how to pass this kind of information from the encoder to the decoder for more effective segmentation. So this is enabled through this kind of skip connection in the UNet. But UNet, it's mostly for UNet is a concept. I mean, passing the information from the encoder to the decoder. It can be of convolutional based UNet, or it could have been through something like a transformer based UNet. So as we all know, recently or down the line 5 years before, transformer has gained a lot of attention. So the unit can also be designed with the transformer blocks. Something like a trans unit that has some CNN layers, then the projection gives it to a transformer layers. And we'll see this how this transformer layer works. Or it could be purely transformer. So the first one, the trans unit, it's a hybrid network, CNN transformer. The second one is a purely transformer based, right? So if you are not very familiar with the transformer architecture, let me do a quick recap. So, okay, I hope everybody is well familiar with the convolutional neural network architectures. So in the CNN, the building block of the CNN is the convolution operation, right? So similarly, on transformer block, the building block of the foundational operation is the self-attention. And the goal of the self-attention, if I have to do a clear distinction between the convolution and self-attention, is that in the convolution, we do the local neighborhood modeling. For example, if we have a convolution operator of matrix 3 by 3, the goal is to learn the neighborhood relationship between those 9 pixels in the 3 by 3 matrix, right? But in the self-attention, it captures the dependencies and relationship across in a global pixel level or the global patches. So it computes a correlation among the features vector in a sequence. And how it works. So basically, if we have a feature map, let's say n by d, after some convolutional blocks or convolutional layers, let's say, uh, it try to project the feature into three vectors, that is the key, query, and value. And these projections could be linear, or there are literature they do convolution, this and that. And after that, the query and the key and query, they are multiplied to form a n by n matrix. And after the multiplication, it is softmax activated. And as we know, softmax is a normalized activation function. So it will try to scale the entire activation values between 0 to 1. So there is a high chance that inside the n by n matrix, there will be few index that has the high value and other value will be low. So that is the saliency map, or that is the attention. And once we have this kind of attention map, it is multiplied with the value to get the enhanced feature map of the from the original one, let's say X. So you get something, a self-attention feature map. And the output feature map has the same dimension as the input, right? So how it is integrated, this self-attention, to a transformer block? So a typical transformer block, it looks like in NLP, it looks like this. So you have an input embedding, and the input embeddings are then positionally encoded. It is added, the positional encodings are added to that. And then it is passes to these three parallel lines. If we see the key, query, value to the multi-head attention, then there are few feed-forward networks, the add and normalization to propagate the information from the input to the end of the transformer layer. These are just skip connections. And so this is a typical transformer block, and then this is given to a decoder. So how this kind of transformer network can be used in the vision, because this is a transformer architecture good for the natural language processing. I mean, if you have a sentence, how to get, if you want to classify a sentence, so this is a network. But in the computer vision, in image domain, we do not have a sequence. So the key thing is how to generate a sequence out of an image, right? So that's why the vision transformer has, it arrived 3 years back, if I recall it correctly, 3 or 4 years back. So the idea is to, it takes the same transformer block of the that is adopted in the NLP domain, but it mostly focused on how to generate a sequence out of the image. So basically, it split an image into different patches, that we call it as the tokenization, let's say. So when you split the image into multiple patches, and you try to order the patches in a sequential manner, then it becomes a sequence. Or if you try to stack the patches, then it becomes a sequence, right? So once the patches are done, the next step is to flattening the patches. And as the patches can have higher number of pixels, let's say each patch is of 16 by 16 matrix. So we have a 256 dimensional vector. Then the idea is to produce some lower dimensional linear embedding from the flattened patches, then adding the positional values. So this is the first patch, second patch, this and that. And then it is given to the transformer encoder. And the transformer encoder on the right, we can see that after the patch embedding, there is this normalization, multi-head self-attention that we discussed before, and end of the block, there is MLP. And this network can be, we can stack this block L times. So the network is highly scalable, right? And the end of the transformer block, there could be MLP heads to do some classification, let's say ImageNet data set, this and that, right? So if I have to clearly draw a line between VEET and CNN, so VEET has more similarity between the representations obtained in the shallow and deep layers compared to CNN. And unlike CNN, wheat can obtain global representations. For example, global, I mean by all pair relationship between the patches. But it might fail somewhere in the local representations. And in the wheat, the skip connections are even more influential than the CNN, the typical ResNet, and it can substantially impact the performance. The skip connections are, I mean, from before the norm to the after the self-attention, right? And the wheat can retain more spatial information than CNN because of the global relationship modeling rather than just local. And it can learn high quality. Thanks to this, it can learn high quality latent representations in large amount of data. And the most important thing is wheat is scalable and it is efficient to compare to CNN. For example, if we have a bigger data set, so the entire story of the foundation model, I think it started with the scalability concept. So if a model is scalable, it's more scalable and it can fit to a huge amount of data set, then the pre-training will be more effective. So WIT has this kind of scalability um, functionality. That's it. So then if we have to rethink about this common method that people have already used for segmentation based on the transformer. So these are mostly task specific models. Let's say you have designed, let's say somebody has designed this U transformer or trans unit. Then they have trained it on some data set or the data set of their interest. Then it becomes a task specific model. So this model is good for that particular task. But what if we have a foundation model that has that can be transferred to many other tasks, right? So what do we want? A task specific model or foundation model? So let's see in this in the upcoming slides. So as I said, the task specific models, these are mostly tailored for specific task or data sets. And it might require you to starting from the scratch or random initialization. And it needs substantial if effort to train on the new task or to understand the new data set. Right. But the foundation models, these are pre-trained on massive amount of data sets, and they can perform well across a wide range of tasks like with minimal task specific fine tuning. So these models have pretty high amount of generalization abilities. They are scalable because the networks are based on transformer. And despite this, they have high downstream transferability. Maybe if the model is not directly applicable to some specific task, let's say because of the large domain game, but if we fine tune with smaller networks along with the foundation models, it can adapt the new domain pretty quickly. And these foundation models are this can scale to large pre-training data sets. Like as we know in the recent era, the social media, all these things, we have a huge amount of data collections every day, maybe petabytes of data. If we want to leverage those kind of information, we need some large scalable model, right, to learn from those, not to overfit or underfit on the large amount of data. So you need a scalable network. So let's see some of the popular vision-based foundation models, right? So here in the today's agenda, I thought of discussing the three popular foundation models that can be more suitable for medical image segmentation problem statements. So the first one is the mask autoencoder. So this is a paper from the Facebook AI research. And the second is the OpenAI GLIP, the vision language models, and the SEM, the segment anything model, mostly for the general purpose object segmentation based on some prompts, right? To begin with, let's start with the mask autoencoder. If you have some questions, I'm ready to take maybe in between, or I'm not following the chat box, I don't know. Uh, Okay, where is this chat box? Do I have any questions?
Yeah, you
Okay,
can you can just check their chart. They will
all right.
recite their comments only on the chat box.
If reads can learn global and local representations vector from shallow layers, how might this influence the design of lightweight models for the AS device compared? I think this is a great question. So the question is, if it can learn global and local representations from shallow layers, how might this influence the design of lightweight? Okay. So for the AS devices, this is true. This is, it really depends upon what kind of AS device the user have. Nowadays, even edge devices can run some amount of transformer networks because of the better optimization with the hardware things. But if not, let's say that we have just a really basic uh, edge device. So the popular concept there is the distillation. So one can really distill the information or pass the information from these large transformer models to smaller traditional CNN networks, and it will enhance the performance of the regular CNN substantially by doing some distillation of the weight model. I think I answered the questions. The first one. Second one, does transformer-based models provide accurate segmentation on very small lesion of MRI scans? Does the patch-based approach of transformer model increase class imbalance and reduce segmentation accuracy for very small? Okay, this is also another very interesting question. So transformer-based, okay, for the small region in the small segmentation region. I think this is a very critical problem still, I guess, because of the patch-based thing. So it still needs some amount of tailoring in the wheat architecture to effectively segment this kind of smaller patch in the MRI scans. So, okay, this is more specific to the subject area. So maybe, uh, the literature can answer more appropriately on this. Okay, when to go for using foundation model rather than using CNN? Okay, so transfer learning, if you are using the CNN and the transfer learning, I think there is a good amount of scope for using this kind of foundation models, because in the transformer learning, you still use some amount of, let's say, VGG or ResNet 50, ResNet 150, some CNN model pre-trained on ImageNet, but those are pre-trained on supervised, uh, those models follow supervised pre-training, right? So that has limited learning ability. So why we are doing the transfer learning? This is basically to enhance the image representation ability of the model. So we take the pre-train from the ImageNet, and let's say you try to fine tune or do the transfer learning on your target data set. But the foundation models, these are mostly self-supervised pre-trained. So it has more general image understanding than the regular supervised or the image to class level mapping based this kind of model, right? So that's why the foundation models are far more better than this kind of regular CNN pre-trained models. Okay. Third question, if my understanding is correct, then attention modules are often very dense and may learn very. Okay, redundant information. Is there any research on this? That's true. That's true. That attention models are very dense, and it can encode you some amount of redundant information. And that's why, if we see a lot of these days the llama models, why there is this hallucination on the GPT or the llama, because the backbone is the transformer models, and they induce or they infuse a lot amount of redundant information. So the minimizing the redundant information is also a critical research. So there is this kind of uh, something like differential transformer is there that can reduce some amount of redundant information in the transformer. Okay, but those things has to be experimentally verified, and I have no experience on that. Right. Okay, if the data is limited, should one go for using complex foundation model? Okay, that's a great question. Maybe I'll answer these questions. I'll not answer these questions right now. In my upcoming slides, I'm gonna answer. If the data is limited, how we gonna use this complex foundation model, right? Okay, I hope I answer a couple of questions. I'm going back to my slides. Okay. All right. So as I was saying, this mask autoencoder. So these foundation models are self-supervised. So the difference between the fully supervised and self-supervised is in fully supervised, you have a model, you input a image or video or whatever. End of the model, there is a classifier network, and the classifier is learning some bounded class levels. So it is a one-to-one mapping function or one-to-few mapping function for in a multi-level scenario. So each image has a correspondence class level. So if you have a mapping this kind of scenarios, then this is the fully supervised setting of the class level centric. But in the self-supervised, there is no class level. You just have the data. You just have the bunch of images or the videos. So how to leverage only the videos or images to learn, still able to learn some sort of general image representations or general low and high level feature. So this mask autoencoder, this is a simple approach. People, all those who are aware of the autoencoder architecture that has an encoder decoder structure, they might be able to follow these slides pretty easily. So the task here is to predicting the pixel value for each of the masked patches with a training objective is mean square error. There is a common loss function for all autoencoders. So here you have an image, let's say image of a bird. The idea here is to you first tokenize the image because the encoder and decoder both are transformer based. You need to convert the image into a sequence. So first tokenizing the image. And after the tokenization, the idea over here is to mask the tokens. So not by masking 10% or 5% of the tokens, by providing a huge amount of masking. And with the remaining patches, you try to stack them, pass it to an encoder, get the latent vectors. And with the latent vectors, you try to pad some tokens for the unmasked patches of the input. And with this concatenated latent vector, that is the embedding from the encoder and the masked tokens, the decoder tries to predict the entire image, the image containing all the tokens. And this is optimized by the mean squared error loss, right? So how it does this kind of thing? So MAE they have a large encoder. As I say, these are the scalable networks. So they have a large encoder on the visible tokens, and they have a small decoder on all tokens, like visible and non-visible tokens. And there are some projection layers to connect this kind of encoder and decoder, right? And the key feature of this kind of MAE is high masking rate, as in something around 75%. And the model, it works the best with 75% masking rate. And as it has a large amount of a large amount of data, big network, the network is asymmetric. So if you want to have a feasible amount of training, so one needs to take care of the time required for the pre-training. So due to this kind of asymmetricity in the encoder and decoder, that is the large and small, it significantly reduces the pre-training time, right? So how it works, if I have to go in detail slightly, the step one is to random masking. So you divide the image into non-overlapping patches and randomly mask with a ratio of, let's say, 75%, and you try to discard them. After that, you have the visible tokens. You pass it to the encoder, get the latent feature map. So the encoder here is a VIT, vision transform. Okay. And then the adding the mask tokens, here in the after it is latent encoded, and then giving it to the decoder. That is a small bit because it has to be lightweight to reconstruct all the pixels of the all the patches of the image, right? And how do we? So this is the pre-training stage. So you have a big data set. You try to do this kind of pre-training. The downstream transferability is the key. So after the MAE is pre-trained, so this is the encoder decoder is pre-trained, you need to just discard the decoder, and the encoder is self-sufficient for feature extraction with the full image as input. Okay. So during the transferability, you need not do the masking again. You just input the full image to the encoder and get these feature vectors. And those features has the much more information contained than the regular CNN-based pre-trained models. So if I have to show the potential of these MAE models, if the image is patched like this with a ratio of, let's say, 75% to 80%, still it is able to predict a image of a dog, and this is when human can recognize. I mean, okay, this is with the prediction that okay, this is some similarity with the image of the some similarity with respect to the actual image, right? So can you guess this image? I think, okay, I used to ask this in the class. Okay, so here because with the masking input of 80%, it's really hard to guess, right? But when we try to do the prediction with this kind of masking, still it is able to reconstruct the image of a butterfly, right? So here is a critical analysis. So the MAE pre-training, it outperforms the training from the scratch or training from other large-scale data set. If we train it from the scratch, all these VIT models, all the variants of the VIT models, we see that with MAE there is a significant amount of performance gain, at least 3%, right? Okay, so this is MAE is the mask autoencoder. This is a self-supervised learning-based foundation models, and this is optimized based on reconstruction-based foundation model. We can say that because it tries to reconstruct a image uh, in a form of, let's say, random masking, and it tries to generate the actual image in the pre-training stage. So it is a reconstruction-based foundation model. So the second type of the foundation models is the contrastive based, and one of the popular foundation model is the vision language, the CLIP, the contrastive language image pre-training. So it basically applies a contrastive learning between image and natural language sentences, right? So this method is quite popular in recent days. So so during the pre-training stage, what they have, so they have two encoders because this is language and image. So you have an image encoder. The image encoder could be the VIT, the vision transformer, or it could be the resonant, right? So it takes an image and a text pair. So for the text pair, there is a text encoder. And from the image encoder, it gets a embedding vector for each image. So if you have n images, you need n text pairs. So let's say there is an n image and text pair. So you get a n image embedding and text embedding. Then it tries to compute a similarity matrix, which is optimized by the contrastive learning. And it tries to assign the highest correlation to the image pair with its corresponding the image with its corresponding text pair, and it tries to assign lower similarity values to all of the text pair. Similarly, for each text pair, it tries to assign the higher similarity to the corresponding image, and it tries to assign lower similarity values to all other images. Okay. And after this kind of similarity learning, how to use it for the downstream uh, predictions. So you take an image, this, and you try to say that this is a photo of dog, let's say, and if it gives a the similarity to a particular text token, then you say that this is a photo of this, right? So this is for the zero shot prediction. So how this kind of pre-training, so the key things lies in the pre-training. So how this pre-training is done, let's see that. So, okay, the key, it lies with the contrastive loss. As I say, each image predicts which caption matches, and this model is pre-trained on a large-scale training data set that has 400 millions of image and text pair that is taken from the internet. Okay, and these are the general images. So, and the clip contrastive learning, it looks like something like this. Okay, why there is this missing things? All right. So this is a simple contrastive learning between the image and text embedding. So if we see that, so this is a typical contrastive loss on the top. If we have, this is the image, it tries to enforce the similarity between the image of I with the text of I, and it tries to discourage the similarity between the image of I with text of J. Similarly, for the text of J, it tries to match the similarity with the image of J, and it also tries to discourage all other dissimilarities with the image of I that covers from I to N, right? And so these are two bidirectional or two direction contrastive loss. I mean. So this is a typical example of how this zero-shot transferability happens, and that this transfer learning happens without seeing an image. If you just give a prompt to the clip model, okay, I want an image of this, so it will pop up an image of that particular class. Okay. So it basically gives you an image that has the maximum amount of similarity with respect to the prompt or to the image, right? So if we see that the clip model, it shows a very competitive performance in terms of zero-shot performance with huge diversity of the data set, starting from the Stanford cars, Kinetic 700, everything. But it has some amount of domain gap to the, let's say, for the MNIST, the performances are minus 10%, or for Kitty distance or Eurostat, the performances are pretty low. So on many data sets like ImageNet and Kinetics, the models are performing well because of the pre-training data set, because the pre-training data set is taken from the internet or taken from the web. But the data sets that has large domain gap, MNIST, or maybe in this case, the medical data set, it might suffer the domain gap problems, right? So again, in terms of the clip model is it is more robust to the distributional shift. So for example, if you show an image of banana in different varieties, the real banana to the enemy or to the sketch, still it is able to give high amount of detection accuracies. So in terms of distribution shift, it is pretty well. So, okay, as we said, this is good for the, if I have to summarize this clip model, clip model is pre-trained on carefully filtered or more clean image of more clean data set of 400 million image and text pair. And therefore, they say that if you pre-train on a more clean data set, the pre-training or the learning ability of the model is more accurate for the transferability. But there are a few limitations. If you, one of the limitations right here is that I got it from the internet, is that okay, if it is a image, if it is a fruit, it's correctly say that okay, this is this fruit. But if you try to attach uh, a paper with written this some other text, it will, because of the language kind of the influence by the language, the text encoder, it might misclassify to some other classes, right? So this is one of the limitations of these models. But what interesting thing is over here is to use this image encoder, because clip has two, the image encoder and text encoder. For the computer vision people, can we use this kind of image encoder to transfer more RGB features to our downstream task? So that could be more interesting. And okay, how many time I have? Okay, I need to go slightly fast. The next one is the segment anything model. I think this is the model that interests more interesting for the image segmentation problem statement. So here the idea is to the segment anything model is designed to segment any kind of objects in the world based on some prompts, whether you give the prompts based on some points by clicking in the image, or you give a bounding box, or you try to give a mask, random mask, or you try to prompt with a text. So along with the image, if you give any of this kind of prompt, it will precisely segment that particular object of interest. So basically in the SAM model, what you have it takes the image that goes through a image encoder. Then there is a prompt, it goes through a prompt encoder. End of the model, there is a lightweight mask decoder, and that gives you a varied mask, right? And this is trained on this SA 1 billion data set, and how this data set is being curated. So the data set is being curated iteratively. And because if you want to train a model for masking, and if you want to generate 1 billion plus mask, I mean, this is quite complex. So what I do is like, okay, they first take a model, they do some amount of annotation, train the network, generate the predictions. Then there is this human in the loop to do the rectification of the masking, and then again they train the model. So once they do this process iteratively to generate more cleaner version of the annotations for this SA1 billion data set. So if I have to zoom in into this SAM model, so there is a SAM and image encoder that is mostly based on the width. The image encoder gives some latent vectors, and then there is this prompt encoder. Maybe it is a point, bounding box, a text that goes through some prompt encoder and with the mask decoder. Then for each of the objects in the scenario, you get the segmentation mask with a confidence or with a score, right? So the components of the SAM, as I say, the image encoder, a WIT model, just producing one embedding for segmentation, and the prompt encoder, three prompts, and the mask decoder, it tries to take the prompt token and image embedding through transformer decoder and predicts multiple mask candidate. Okay. And this model, the same model is pre-trained on this SA 1 billion data set. And this is the, as I say, this is trained based on model in the loop design. So the data annotators use and fix the output of the SAM model iteratively. And based on this, they try to retrain the SAM and repeat this process to bootstrap the performance in the pre-training stage. So, as we have discussed these three foundation models, what is stopping us from using this kind of foundation model for regular image segmentation? So the first one is the large domain gap. So as this tutorial or session is going mostly on the medical image part, so the medical images are far away different from these models pre-training. So there exists a significant difference between the natural and medical images. The second one is the inferior transferability. So in the medical domain, the data is limited. So there is limited data, there might be limited supervision. So by following the traditional full fine-tuning strategy, for example, if you want to do the transfer learning with a pre-trained CNN by adding some linear layers, it might not work here because the model itself is quite large. So while fine tuning, there is always a trade-off between the number of parameters to optimize and what is the scale of our data set. If we have higher number of parameters and lower amount of data, the model will underfit. If we have a low amount of model parameter and huge amount of data, again, the model will try to underfit or overfit. So there has to be some balance between the number of parameters to the samples we have for the training samples. So the regular or traditional fine tuning, it will try to do overfitting or forgetting, or maybe it can reduce the or degrade the features, right? And this is increased computation cost because the SAM model, if we take it as an example, it takes 4 times higher resolution input images compared to the classical width. So when we have higher resolution of images, we have higher number of patches. So we have 4 times the number of patches. So then it increased the computation cost of in the fine tuning by a factor of 4. And then in the SAM, they rely on some sort of prompts, right? Like the points, the bounding box, or the text. So requiring this kind of prompts, okay, it can produce a segmentation mask. But in most medical cases, the segmentation models, they simply rely on medical images. The output, they don't have any prompt, right? So how to take the advantage of these foundation models like SAM and still use on the medical image segmentation? Let's see in the upcoming slides. So this is one of our recent work. So I try to mentor a student here. That is the SAM Mamba for zero-shot polyp segmentation. Okay, I know little about this polyp segmentation. Okay, this polyp segmentation is highly relevant for this colorectal cancer, and segmenting this. Okay, during the chart, someone was asking about how to segment the smaller regions in the image. So that is also being taken care. We can see here in this work by global feature relationship, and it might not detect something like complex and tiny polyps, and may fail to generalize to unseen data, right? And transformer based, they have the because they are mostly focused on global relationship, they might have limited capabilities in the local contextual information for the smaller polyp region. And then there is SAM. There are also a couple of methods that they use SAM for polyp segmentation or other medical image segmentation task. It has impressive zero-shot generalization, but it has limited performance when directly applied to polyp segmentation because of the domain gap, and fine-tuning it on limited data is it is not effective, right? So towards solving this kind of issue, the SAM Mamba is proposed. So the SAM Mamba, there are three key components of the SAM Mamba. One is a SAM model itself. Then there is this Mamba prior module, and there is an adapter network. So how to efficiently fine tune this kind of model uh, is a critical challenge. And then there is this adapter based fine tuning is there that can take the frozen wheat block, and in each wheat block it can attach another adapter network which is pretty lightweight, and it helps to refine the attention maps inside the wheat block, and thereby it can adapt faster to the smaller data set or small scale downstream task. So in the input, you have a image. It takes the SAM encoder. From the SAM encoder, it passes through the Mamba prior. It goes to the adapter network, and then it get injected to the SAM encoder again. And the end of this encoder network, then there is this one latent vector, let's say 1 by D, that goes to the SAM decoder. So here we try to attach another classifier network. Okay, maybe we can discuss it slightly later. So if we have to zoom in this encoder part, the Mamba prior module, it directly takes the image without patching, but the same encoder is based on width, so it do the tokenization, patch embedding, then it passes through each of the width block. And before each wheat block, it takes the input, pass it to the adapter, and in the first adapter layer, there is this Mamba prior. The goal of the Mamba prior is basically to bridge the domain gap between the pre-training of SAM with the target domain, the polypressure, right? Right from the beginning. And then the adapter networks are connected sequentially, and there is an adapter after each wheat block, right? And the adapter network, it looks like this. So there is two sequential cross attention. The key and value, let's say in the first case, it comes from the Mamba prior module, and the query comes from the wheat block. And the output, the enhanced feature vector, is directly injected to the outgoing wheat block. And the second one is connected as the query and key value coming from the wheat. And goes to the next adapter. So how this Mamba prior model is able to bridge the domain gap between the SAM model training the polypressure. So it has two things. One is a multi-scale decomposition. So it tries to decompose the image into three different scales to gather different amount of context for the polypressure, and it tries to stack them to create a feature pyramid. So, and then we pass it to some saliency pool like max pooling and context pooling, let's say average pooling. And then it is passes to a Mamba block. The Mamba is the recent sequence modeling. This is lightweight. It has far below the parameters compared to a transformer, but still it can able to do the sequence modeling parallelly. Okay. So when you have this kind of feature pyramid from the low level context to the high level context, the Mamba can orderly encode the relationship between how the context of information is being flowing from the low level feature pyramid to the high level, right? And end of these two Mamba blocks, the resultants are concatenated, and they are of course keep connected, multiplied to allow the information passing through to the next block. And then we have this enhanced feature pipe, and this is input to the adapter network. Okay, maybe I have discussed all this in the couple of next slides. Okay, then there is this another critical aspect of this SAM model is that it really depends upon some sort of prompts. Either it is point, bounding box, text, or some random mask. So how do we do without having any prompt in our data set? So basically we follow two-stage training. In the stage one, we take this image, we use the SAM encoder, and then we attach a small decoder layers, something like a decoder of a unit, and we optimize this network. Okay, in this case, we might not get the best accuracy, but we will generate some amount of pseudo mask. In the second stage, we freeze this f theta, let's say this small decoder, and we unlock the same decoder. So when you pass this to the small pre-trained decoder, it will generate you some pseudo mask. You give it to the we give it to the prompt encoder, and then it enhances the SAM decoder performances. Right. So maybe these are these all these texts I try to skip due to time constraint. So if we see that, if we compare that, even for a smaller polyp region, the SAP Mamba is precisely able to segment. And this is due to the bridging the domain gap between the SAM pre-training to the target dataset and the two-stage refinement approach to generate more high-quality prompts, right? So we have more diversified, we visualize all diversified types of polyp regions, and we can see from a larger region to the smaller region, still it is able to detect. Right. So how this two-stage training is helping? So if we look at in the first stage in the encoder, as I've said before, it tries to capture the low-level semantic cues or the more fine-grained semantic cues. But the decoder part, as it is taking the mask from the pseudo decoder or the pseudo mask. So if we can see the activation map in the decoder layer, still it is able to more appropriately correspond to a region where there is this polyp, and thereby we have the best quality, let's say, segmentation mask. Yeah. So if I have to summarize, the SAM Mamba, it outperforms traditional CNN and VEET models in both quantitative and qualitative approach, and it has demonstrated excellent adaptability. So if you're interested in this work, maybe you can refer to this paper. And in future, we are trying to generalize with more efficient Mamba modules, right? So then there are one more that tries to, this is a hybrid foundation model, if we can say, or this is a clip-based segmentation model. So what they have is they have an image that goes through a vision encoder, latent embedding. Then there is this adversarial module. And from the text, so the adversarial module, it tries to generate two masks. One mask corresponding to the, let's say, causal, and this is, let's say, 1 minus m is the founding. And this masker is just like convolution and sigmoid operations. Okay. And after these two masks, let's say m and m dash, they take the text as the input. They have the text, and it goes to the text encoder. The text encoder gives a text embedding, and only in the decoder they try to multiply the text semantic feature to the both of these two decoder layers, and then they optimize this with this loss of C and lambda loss of S. So one corresponding to the region in the chest and one corresponding region other than the chest images. Okay, so if you're, this is a Mikai 24 paper, so if you're interested, feel free to read this paper. So, and yes, there is this hybrid model that is the clip and SAM model. So in the first step, they first adapt this clip model to the medical data set. Let's say they have an image encoder, they have the text transcript somewhere, and then they try to learn this kind of similarity matching. And once this clip model is fine-tuned, they use it in the SAM model to generate the pseudo mask. So in the SAM, they take the medical image, they have the image encoder. The image and the mask decoder, it takes two things, one from the image, one from the mask. So the masks they are generated from the GradCam. So they try to prompt this kind of fine-tune clip model with the text prompt, and they get the GradCam. From the GradCam, they generate the bounding box, and bounding box is used for the prompting the encoder. And this is mostly, this model is mostly used for weakly supervised segmentation. And if you don't have the exact ground truth, yes, this could be one of the approach. So briefly, what we have discussed, we didn't go in detail into a lot of things, but the idea is to ignite this kind of techniques to the medical imaging task. So we started with this transformer model, which is far more has a far more scalability potential compared to the CNN models. And thanks to this, these transformer models are it has been the integral part of all these foundation models. And then we discussed something with the mask autoencoder, that is reconstruction based foundation model to uh, reconstruct the masking patches in the input image. And then we discussed the clip based vision language model that learns the similarity between the image and text pair. And then we see this kind of SAM model that can generate the segmentation mask for any general purpose images with an input image and a prompt. And at the end, how we can adapt this kind of SAM model to the medical domain with limited data, limited resources. We discussed the SAM model. So I hope few things are at least clear. So maybe if I have some questions, I'm happy to take. So I try to create these slides from all the resources in the internet. So these are the references. And thank you. Okay, I have to see some questions.
So, thank you so much for your wonderful talk on foundation models and its uses in medical image segmentation. So participants have at least got the idea behind the use of foundation models. They can explore now the foundation models in exam and how it can be adapted to the medical image segmentation problem. So there is one question, so you can take and then.
So there is a new question.
You can discuss other questions during the your hands-on sessions. Yeah.
Okay, so which segmentation is more effective for accurately delineating lesion with fuzzy and ambiguous boundaries? Okay. So lesion and so I think this is also a very great question, and it when you have a fuzzy boundary, this is true that the foundation model might suffer, and it really depends upon the task. But as we did this kind of thing in the SAM Mamba to generate first pseudo mask and then prompting this pseudo mask to the decoder. So if we can generate some high quality pseudo mask as a prompt, then definitely we're gonna unlock the potential of the SAM model to this ambiguous or fuzzy boundary regions. I hope it answers the questions to some way.
Yeah. No problem. So they can continue. I mean, asking queries, and you can interact with them during your hands-on session. That will be purely interactive session. So at 7:10, yeah, up to 1 hour. So we are right now having another session. So thank you once again for a wonderful talk and giving your insights on the foundation models. I hope it will be useful participants for all of you.
Always pleasure to do. Thank you so much.
So we'll again meet after 1 hour. I mean, it's 7:30.
All right, sir. Okay. Okay. I'll take your leave. Okay.